This is the Virtual Reality Optical Design System and was created to model optical systems in an informative and modern way. We were tasked to create this system by Area Optics, an optical engineering company that specializes in polarization ray tracing software. By utilizing Polaris M, Unity, and Mathematica, we were able to create groundbreaking, multifaceted optical design software that can be used in both commercial and educational settings. Optical systems are not easily represented in three-dimensional space. Combining an optical design program with Unity to display optical systems in virtual reality has never been accomplished before. This proved to be a challenge to complete, but we feel that we more than rose to the occasion.
Our system is designed to explore the potential utility of Polaris M and Unity to create a prototype VR education software for optical engineers. To demonstrate this, the virtual reality system comes equipped with a host of features for interacting with and rendering optical systems, with support for displaying ray paths, polarization ellipses, ray reflection/refraction, polarizers, and retarders. This project makes use of a virtual reality headset and controller so that users can view optical systems at all different angles and in high detail from close-up views.
The modular nature of our system means that the virtual reality system can support any number of optical elements in a scene, which allows for the potential for a user to design any optical system. In future work, the virtual reality system can be used to emulate entire lab scenarios with known off-the-shelf parts for students and designers to perform virtual experiments with.
Our project makes use of several different programs communicating with one another. Polaris M is a polarization ray tracing package used to generate optical systems and polarized ray tracing simulations. Mathematica is a high-level programming language containing many useful engineering design packages. Unity Link is a software package inside Mathematica which plays the role of a bridge between Mathematica and Unity. Finally, Unity is an architecture used for developing and rendering interactive 3D software. Early on in development, we knew that communication between Polaris M and Unity was a top priority. We decided on using Mathematica's Unity Link package after experimenting with it and finding how intuitive it was for us to use with Polaris M. In order to use Unity Link effectively, we needed to design a parser function to efficiently interpret the data being sent from Polaris M and visually represent it in Unity. The pipeline between Unity and Polaris M was the focus of most of our development in this project.
Each scenario is first modeled in Polaris M and loaded into Unity. Users can manipulate the Unity optical systems using a VR controller. When a user has finished editing optical systems, the updated position and orientation data is sent from Unity to Polaris through the Unity link. The resulting system is then modeled and a new ray trace is performed inside of Polaris M. This ray data is then sent back into Unity for rendering. 3 scenarios, each with their own personalized optical system, were designed to demonstrate the capabilities of the virtual reality system. The virtual reality system features these scenarios inside of Hikari-kan, Gallery of Light, a virtual art gallery we created to immerse the user in the experience. We decided to make each scenario have a success condition that users must achieve to advance to the next scenario. We came to this decision because we felt it would increase the user's engagement with the virtual reality system. Each of these 3 scenarios will now be shown and discussed in further detail. Polarized light rays incident on mirrors will have their polarization state changed when reflected off of a mirror. The goal of the first scenario is to demonstrate this principle by requiring users to turn a horizontally polarized light beam moving in one direction into a vertically polarized light beam moving in the opposite direction using 3 mirrors.
In this scenario, it was very important to clearly communicate the polarization state of the rays. To achieve this, red polarization ellipses were rendered at the midpoints of each ray to visually represent its polarization state. These ellipses were drawn using the polar form of the electric field data taken from Polaris M's ray tracing calculation.
Dove prisms can be used to rotate rays at different wavelengths. In this scenario, each wavelength is represented by a different color. Rays are being emitted in an expanding ring pattern and need to be brought into focus. To do this, users need to utilize the lenses and prism to focus and rotate the rays in such a way that each ray is incident on its color-coded target.
The Dove prism system requires very precise alignment. However, to save playtime, we decided to add a snapping feature for the user. The optical elements will snap into place and remain locked to only move along their optical axis. Once snapped into place, users can pull on a pair of levers to precisely position the optical elements in the scenario.
Retarders can modify the polarization state of rays that pass through them. This effect will vary as the axis of orientation of the retarder is changed. In the final scenario, a ray with a random polarization state is coming in from the left and passing through two retarders. The first retarder is a quarter wave retarder that is often used to convert a circular polarization state into a linear state and vice versa. The second retarder is a half-wave retarder that can rotate the direction of linearly polarized light. The goal of this level is to convert the incident random elliptically polarized light into vertically polarized light. It can be achieved by adjusting the orientations of these retarders. The ray passes through a vertical polarizer before entering a battery, causing it to charge. The rate of charge is proportional to the flux of the incoming light through the polarizer. The scenario is completed when the battery is charged 5 times. Users will need to increase the charge rate of the battery by maximizing the flux of the ray through the vertical polarizer. Every 20 seconds, the polarization state of the incoming ray changes, meaning users will have to stay active and respond to the change in the scenario.
The original plan for Scenario 3 involved continuously updating the incident polarization state, in our case, 90 times every second. This meant that the ray trace calculation needed to be done every 0.011 seconds, which posed an issue due to the time delay involved in data transfer between Polaris-M and Unity. We instead opted for generating random incident polarization states every 20 seconds, and updating the traced rays when the user is done adjusting the orientation and releases the object. This allowed for more than enough time for data to be transferred, as well as allowing the user to have enough time to find the correct orientations for the retarders. Using virtual reality, optical designers and students can observe how light rays and polarization will propagate through a system in close detail. We believe this will greatly enhance the optical design process, allowing them to rapidly collect complex spatial information.
We would like to thank our sponsor, Area Optics, for making this project possible, and you, the judges, for watching our video. We hope that you enjoyed the video and understand the potential of this project for future work.